Right, we are now moving on with our syllabus. So today we want to look at equation of state. After that, we might also proceed to kinetic theory of gases. So under the equation of state, the first one, we want to understand the gas laws. Uh, Understand that PV is proportional to T, where T is the thermodynamic temperature, which is in kelvins. Then after that, we want to recall and use the state of the equation of the ideal gas, which is PV is equals to nRT, where N is the amount of substance or the number of moles, and PV is equals to nKT, where N is the number of molecules. And you also want to recall the Boltzmann's constant K, which is given as R divided by the Avogadro constant. So we will look at that as one topic with this kinetic theory of gases. Under this, you need to state the basic assumption of the kinetic theory of gases. We also need to derive this formula. They are saying explain how molecular causes the pressure exerted by the gas and derive. We want to derive and use the relationship PV is equals to half 1/3 N M C squared, where this C squared inside these brackets is what we call the mean square speed. And also we also need to take note what we call the root mean square speed. That will be the square root of that. And also we need to relate using these equations. We need to relate the two equations, because here we are saying PV, it's PV. So if you equate nKT is equals to this one, we'll be talking about the kinetic energy. Right? So we need to equate. So now let's move on to this one. So under this, we are saying this one is the equation. This one is the equation of the state equation of the state of an ideal gas. All right, this one. Let me try to find which pen can I use. It means this one. So this one is what we call the equation of state of the ideal gas. PV is equals to nRT, where we are saying for an ideal gas, it must satisfy this equation, where we are saying P is the pressure of the gas, V is its volume, T is the absolute temperature in kelvins, N is the number of moles of the gas, and R is the molar gas constant. So the equation is what we are referring to, the equation of state of an ideal gases. This one is an ideal gas, right? But normal under circumstance, we are saying real gases normally obey this equation, except under extreme low values of temperature or very high pressure. Because we are saying this equation is meant for ideal gases, but when we are saying in a real situation, we have got what we call real gases, and they are saying those real gases tend to obey this law, though at some extreme values of temperature and some extreme values of high pressures. The gases, that law seems not to obey this one. So for gases at moderate values of temperature and pressure, it can be shown experimentally that with what we call the Boyle's law. This Boyle's law, it states that a pressure is inversely proportional to volume, meaning to say when the pressure is increasing, you would see that your pressure, if your volume is increasing, your pressure will decrease. Then we also have what we call Charles' law. Charles' law, it states that volume is directly proportional to temperature. When temperature increases, the volume will also increase. Then we also have what we call the pressure law. The pressure law, it says pressure is proportional to temperature at constant temperature. So here we are saying, here we have a constant. Our constant here, it will be our constant here is going to be our temperature, and here our constant is going to be our pressure, and here our constant is going to be temperature, meaning to say the first under boys it will be P, and if you remove the alpha, you are now going to introduce the constant, that is the temperature now. So you're saying our temperature is now constant under that. And also for the second one, Charles law, volume, and you are saying our pressure is going to be our constant, so our P is our constant, and multiplying it by, and under this one we are going to say P is equals to T, because we are saying our constant already is the temperature, so it's T. So these are the graphs. These are the graphs for Boyle's law. This one is the graph for Charles law, and this one is the graph for pressure law. But for Boyle's law, one can draw this because we are plotting 1 over V against pressure. But we can really plot. We can plot. We can plot the graph of this Boyle's law. It can be used inogona where also kuti uku ndokune kuine pressure ukuti wataisa volume, where we are saying as the volume increases, as you can see, the pressure will decrease, so it will be something like this, decreasing that is if you have volume here, not 1 over V, and if you have a pressure, our graph will decrease inversely, because it is directly P and V, they are inversely proportional. So you can draw such a graph. So with these equations, with these three equations, this equation, with this equation, with this equation, and this equation, we are going to combine these three equations, and it is going to form this equation. It is now going to form this equation. PV over T is what is constant, where we are saying the size of the constant depends on the number of gas molecules. So meaning to say doubling the number of gas molecules in the sample doubles also the collisions of the molecules with the walls of the container, and doubles the pressure. So usually R is what we call the R is the constant, which is also going to be referred this constant. They are referring it to what? To R, the molar gas constant. This one R. MO is just a number. Avogadro's number Na. This one we are given in our formula booklet, and we are also going to say, and so the constant is different amount of gas. NRT N is the number of moles present. Okay, let's look at this example. What are they saying? Before setting off on a journey, the air in the tires of the car was at temperature 18 degrees Celsius and pressure of 1.92 to times 10 to the power of pascals. They are saying immediately after completing the journey, the pressure of the tires was this one now. Then they're saying, what is the temperature of the air in the tires? So what we are simply saying here, we are saying we have the volume. We are going to assume, that is our assumption. If a car is moving, we are, as the driver, we are going to say there is no hatina mweya uri kubuda mutai, hanti paunenge uchitofamba nemotikari yako tai rako uchitoziva kuti rine mweya wakakwana, meaning to say the assumption when a driver is driving a car is that the volume of air in the tires is always constant. So that is the first assumption we are going to make. So if our volume is constant, we are going now to use the formula. We are now going to say this PV over T is constant, meaning to say initial PV over T is equals to final PV over T. We are now equating, because we have initial pressure, we also have the final pressure. So we are going to use this equation. P1 is simply saying this one is our it's our pressure one. T1 is meaning to say it's a temperature one. Then P2 it's pressure at T2, and T2 is the time. So we want no, T is the temperature. So but how does a temperature after the journey, that is T2. As you can see here, the volumes they cancels each other, and if you make your temperature T to the subject, you are going to remain with this. Since we are saying temperature is in degrees Celsius, whenever you are calculating this one, you need to convert your temperature to kelvins. So you need to add 18 degrees Celsius with 273, and your temperature will be in kelvins. And pressure at P2, that is the final pressure, is this one, divided by the initial. So it will be temperature, it will be 341 kelvins. So takapuwa temperature iri degrees Celsius, we can convert it back to degrees Celsius, where we are going to subtract with the minus 273, and to get our final answer is 68 degrees Celsius. That will be the final answer for that. Right now, we are now moving on to the kinetic theory of gases under the Brownian motion. We are saying Brownian motion is named after Robert Brown. He was a botanist. So in 1827, he observed pollen grains in water and noticed tiny particles ejected by the pollen grain moving about a random. So here Brownian motion akabva related that experiment to my smoke particles, where the smoke particles we are relating it to the gas, right? So under Browning's motion, he's saying particles of smoke illuminated with the bright light and observed under the microscope. This one is the experiment whereby is observing the motion of particles through the microscope. Here are the smoke particles in a glass cell. So he's saying under that the particles will be moving, jiggling about randomly, continuous, changing speed and direction. The effect is explained by air molecules, which are too small to see by the microscope, bombarding each smoke particles from different directions. The Brownian motion is clear evidence that molecules in gases are continuous and random in motion, and the experiment is the basis of the kinetic theory of gases. So we are saying this one is the general motion of a gas. It moves randomly. We cannot predict the direction of the smoke particles in those right? Let's move on to the internal energy of a gas. Internal energy of a gas. The molecules of the gas have both kinetic energy and potential energy. The molecules of a gas have both kinetic energy because they are moving, and potential energy because there are attractive forces between them. So the sum of all the molecule potential energy and kinetic energy is what we are now referring as to the internal energy of a gas. So if someone say define the internal energy of a gas, we are simply saying it is the sum of all it is the sum of all the potential and kinetic energy of gases. It's what we call the internal energy. But for an ideal gas, if we are saying gas is ideal, we are going to say there are no intermolecular forces. So we have no potential energy per ideal gases. So per ideal gases, all the internal energy of the ideal gas is kinetic energy, because we are going to say for an ideal gas there are no intermolecular forces. So after saying that, if there are no intermolecular forces, we are saying the internal energy of that ideal gas is purely kinetic energy. So under that kinetic energy, we are going to formulate what we call the kinetic theory of gases. So the kinetic theory of gases is based on the model of a gas that has many ideal particles moving about randomly colliding with each other, and the walls of the container constantly changing speed and direction. The theory makes a number of simplifying assumptions about the gases. So these are the assumptions that you should know under kinetic theory of gases. So the first one, we are going to say the gas molecules have negligible volume compared to the volume of the gas as a whole. So meaning to say, we are saying gas molecules edu, we are going to assume that atina volume, that particle pachezvayo, that particle, it's a tiny particle. We are going to neglect its volume. We are going to neglect its volume. Then the second assumption, right? So the second assumption, we are going to say forces between the gas are negligible, like what I've explained earlier. Intermolecular forces. We're going to say there are no intermolecular forces between the gases, meaning to say forces between the gases, they are negligible, except when colliding with each other. So the third assumption, collision between molecules or between the molecular and the walls of the container are perfectly elastic. They are perfectly elastic. Target collisions, perfectly elastic collisions, kinetic energy is conserved. Then the fourth assumption, for an individual gas molecule, the time for collision is negligible. We are going to neglect the time for collision. So we have this container. We are going to use this container to derive that equation. Right, we are going to take this cube where the length is L, L, L. So imagine a single molecule of mass M inside the box L is traveling with a speed c towards the right hand of the, so meaning say tine particle iri apa iri kuuya to this face. That particle of mass M is traveling with speed c to this side. When it collides with the wall, it has a perfectly elastic collision like what we've highlighted and rebounds with that same speed. Those zvatoita pamaelastic collision pachirinoita hit the wall, it is going to rebound with that same speed. So the change in momentum, will be saying what will be our change in momentum when this one is moving, this one will be saying initial momentum minus final momentum, that is our change in momentum. So our initial momentum is mc, and we are saying it is going to bounce back with the same, it is going to bounce back with the same speed. So c, it will be in the negative direction. So that's why we are having this negative. This minus is for changing initial minus final. So if you add the two, we're going to say change in momentum is going to be 2mc. Now the molecule moves towards the left and rebounds and returns, like what we are saying. The molecule will have traveled a total distance of 2l, because when you are saying when the particle moves here to here, it's l, then it bounces back, it's another l. So the total distance being moved is 2l. So now what will be the time taken? You know, from the formula, speed is equals to distance times time. We are saying speed c is equals to our distance, the total distance, that is t. The total distance is 2l divided by time t. We're going to say our time taken. So if you make your time, you have a 2l over c. This one is the time taken. Then now, using the Newton's second law, our Newton's second law, F equals to ma, using your second law, F equals to ma. We are going to say force is the rate of change of momentum. That is the Newton's second law of moment. Force is equals to the rate of change of momentum, and that force here is what we call F. So this one is the force, is the change in momentum over time taken, like we've made T the subject. This one is our time taken, 2A over C. Then if you simplify this, you're going to get this one. So the force is going to be mc squared over L. So what would be the pressure being experienced with this face? We are now saying what is the pressure on the right hand wall. So you're saying pressure is force over area. It's force over area. So our force is this one. This one is our force. We are going to substitute it here and divide by the area of that face. That is length times length, and you have your L squared. So our pressure will be mc squared over L cubed. That will be our pressure, right? So for n molecules, for the number of molecules n moving, because here this one is the pressure caused by just one molecule. So suppose we have n molecules, capital letter N molecules. So the total pressure, it will be that n times this one, where we are now saying it's no longer c squared, where we are now saying it is the mean squares of all the molecules, because there are several molecules here. So we are going to take the mean of those velocities, then square it. That is this value. This is where it coming from. The mean squares of the velocities and the volume, and v is the volume of the box. This assumes all the molecules are traveling in the same direction and colliding with same two opposite faces of the box. So we have managed to derive. You must know how to derive this formula. So we have derived that formula. Moving on, at any one time, as molecules are moving up and down or forward and backward, as left and right, so we must divide by 3. Final divided by 3. Why are we dividing by 3? Kuti tizokwanisa kuzowana the final formula yatiri kuda. Because we are saying at any time the molecules are moving up, first one, down and forward and backward, left, right. So we must divide by 3 to calculate the pressure. So these 3 dividing by 3 is meaning to say we have got 3-dimensional plane. We have this plane of moving downward or upward. We have this plane and also have this plane. So maybe you can say this one is your x plane, and this one is your y plane, and this one is your z plane. So that's why we are now dividing by 3. So that would be our pressure. So we finally managed to derive. Then now you can now make a PV. Then you take this V to this side, you have your PV is equals to 130 Nm, this one. Rearranging the equation can also give this one, or if you arrange this one is the total mass over volume, and we are saying mass over volume is what we are now referring as to the density. So in fact there are several equations of this one. There are several equations. You can take this equation, or you can take this equation, or you can rearrange it, and if you rearrange it, you are going to generate density, where you are saying density is the total mass over. So Nm is the total mass over volume, which is referring to the density. Right, we also have this worked example. It is saying estimate the root mean square speed of air molecules at room temperature. So you must know the estimates usually at room temperature. You must know the atmospheric pressure at room temperature, the density at room temperature of air. These are estimates. They are saying estimates. You are not given the formula booklet. They are estimates. You must know the atmospheric pressure. This one is the estimate. You must also know the density of air at room temperature. Again, this one is the estimate. So using this, we are going to use this formula, and using this formula you are going to rearrange, taking v to this side, and you are now going to have your density. This one is our density, this p like. So, and you make your square mean, the mean square speed, the subject. If you make your mean square the subject, because here we are saying if you arrange, here we are saying we will have our pressure is equals to 1/3 density, and you have your density, and your C, the mean square speed. And if you make your mean square speed, you are going to reach this stage. We are going to say 3 times the pressure, atmospheric pressure divided by the density, and you are now going to get this one as the mean square speed. But if you want the root mean square speed, this one, we are going to say this one square root of this one, and you get 180 meters per second. So that is it. Then you can say kinetic energy of a gas molecule. The kinetic energy of a gas molecule. So comparing PV is equals to 130 mmc squared with the equation of the state, because the equation of the state always say PV is equals to nRT. PV is equals to nRT. So again, we have also this equation, PV is equals to this. So if you equate the two, after equating the two, we are going to play with this one, because you know kinetic energy. Let me write here. You know kinetic energy. For kinetic energy, it's what? It's something half mv squared. So it's half mv squared, something like that. So that's the one. So with this formula, we are going to multiply each term, each side by, we're going to multiply each side by 3. So if you multiply by 3, we are going to remain with the nm, then the mean square speed is equals to 3 nRT. Then after that, we're going to divide by n. So we are going to remain with m, the mean square speed is equal to 3. Then I say open bracket, I'm going to say n divided by n, then r t. Now I'm going to introduce half. So this, if I'm going to introduce half, that will be the kinetic energy. So if you multiply by half, you're going to say it's half. So it's half m, that will be our kinetic energy of the gas molecule. So if you introduce your half here, it will be like 3/2. It will be like 3/2 n over small n over small big capital letter N, then RT. So this one is the equation that was done. So this one can also be reduced to 3 over 2 kt, where we are saying our k is nr over n. That is our k. The one we have referred to the Boltzmann constant. This Boltzmann. So from here to here we can use the Boltzmann constant, where we are saying our Boltzmann constant k is small n, then r, then over capital letter N. That is our Boltzmann constant. Again, we are also given the constant in the formula booklet. So you can finally use this as the kinetic energy of a gas molecule. Kinetic energy of a gas molecule. This one is 3 over 2 Boltzmann constant times the temperature at the molecule when it is moving that speed. Right, I think we have done this. We've looked at this concept on ideal gases, kinetic theory of gases, internal energy of a gas, a Brownian motion. We also have looked at the gas laws, equation of state. So it's under ideal gases. We also have these questions which you must go through. This question right now, book. Saka you are going to go through. Raise your grade. You are going to go through. This one is the question. This one is the question. You can try by all means to answer on your own. Then also check a answer yako. Answer it is given again. So part A, this one is part B. Moving on to part C, part D. And these are now exam questions. These are now exam questions. So you need to go through these exam questions on page 4. So I will explain topic 11 on temperature, but we have also covered something on temperature. So for today, let me end here. Thank you.